Seasons within the concave Earth. I animated the sun oscillating around the celestial sphere every 6 months. So when it's in the Tropic of Cancer, you'll notice that you get 24 hours of daylight at the North Pole and 24 hours of darkness on the South Pole. And conversely, when the sun is in the south, you'll see that you will get 24 hours of daylight on the South Pole and 24 hours of darkness on the North Pole. Originally, when I animated the sun, I did it linearly. There was no acceleration or deceleration, so I couldn't get the equinoxes to line up on March 21st or September 21st. However, when I added acceleration and deceleration, so it's decelerating at the extremes like that, the equinoxes lined up perfectly. And so in nature, you can conclude too that if something is orbiting around something magnetically and it's oscillating north and south like that, there's going to be acceleration and deceleration. In a heliocentric model, you have to conclude that the Earth is orbiting around the sun in an elliptical path. It's very unnatural. You also have to conclude that it's tilting. You have problems with that too as well. And you also have to conclude that it's precessing or wobbling, because it shows that after a year the sun is in a different location against the stars. But if you understand within the concave Earth, it's all taken care of simply by the fact that there's two different velocities. The velocity of the sun and the velocity of the celestial sphere, which is slightly faster than the sun. A sidereal year or a sidereal day is 4 minutes faster than the sun. So after a full year's time, the sun is simply just going to be 1/70th of a degree in a different location than the year before. The planets are all magnetically affected by the sun. So when the sun is inclined like that, the ecliptic of the planets, that magnetic ecliptic imaginary path, is going to be influenced by it as well. There's a real retrograde motion to the planets. It's not just an apparent retrograde motion caused by a supposed spinning Earth. It's simply the fact that when the planets go behind the celestial sphere opposite the sun, they're going to get confused magnetically. So they're going to go the other way for a little bit until they catch up with the sun's influence again, and then go the same way that they were going before. Mercury and Venus, they're going to be orbiting the sun. So when they go behind the sun, they're going to get confused as well. So that's how retrograde happens within the concave Earth. The Milky Way band, it's a band, it's not a spiral galaxy. It's actually a literal band that separates the celestial sphere into two different hemispheres, two different magnetically influenced hemispheres that actually steer the sun. So the Milky Way band has a function. So when the sun crosses that galactic plane every 6 months, it's also exhibited by the Ulysses satellite. They show that every 6 months the sun is oscillating back and forth. So when it crosses that plane, it steers the sun in the other direction. Like when it's up north like that, it's going to steer the sun south, and then conversely the same when it goes down south. When the sun goes down south, when it crosses that plane, it's going to steer the sun back up north. So it's all being influenced by that dividing line, that Milky Way dividing line. It has a purpose, it has a function. Everything works within the concave Earth. Sunlight is bending around the inside of the Earth. That's how we get lunar eclipses. There's an opposite funnel-shaped void area opposite the sun. When the moon goes through that void area, it gets eclipsed. North or south of that void area, it's just simply going to be a full moon. So everything works in the concave Earth. You've seen my animation here, I made it a wide angle, so I wanted to include everything, so that's why it kind of looks kind of funky, but it's Occam's razor. The simplest answer is always the best answer, so.